Continuing with the topic, first we have done estimation and units, and then we did the next chapter, which was about measurement of length, mass, time, and volume. Now let's talk of experimentation, which is the third and last chapter in the topic of measurements. See, we have done all our measurements with the due precision, with due precaution, and we have got a lot of data from that experiment. That data needs to be presented in a form that the reader who reads that particular data or goes to that data is able to understand the conclusions of that experiment. And what we are going to learn today is how to present the data using tables and graphs and how to analyze the graphs. So we did all the hard work with all due precautions and using the best instruments, having the best accuracy. We avoided all sorts of errors. Now we should be equally diligent in recording and presenting the data that we have gathered. So, what are the steps in recording the data? When you measure one quantity using one instrument, then show all the measurements of that quantity in one table. Therefore, separate table for separate quantities. For example, if you measure the radius of a bob using vernier calipers and time period of the oscillation using a stopwatch, then there are two different quantities, that is the radius of the bob and the time period of oscillation. So show them in separate tables. That is the first thing. Second, when you build that table, on top of the table indicate the instrument used and its least count, and if there were any zero errors that you observed. On top of the table indicate what instrument you use. The data that is presented, this is a very important point. It must be as per the precision of the measuring instrument. Like suppose you use a meter scale to record a length and you say 1.7 centimeter, right? That is fine, but you cannot say 1.73. You can't add the second digit after the decimal in centimeters because the least count of your instrument is limited to zero point 0.1 centimeter, that is 1 millimeter. And therefore, if it is limited to zero point 0.1 centimeter, how can you talk of something which is 0.01 centimeter? That is the second digit in the centimeter. So, whatever data that is presented should be consistent with the precision of the measuring instrument. Don't even add extra zeros after a decimal. Suppose you have some data which says 1.7 centimeter. Don't write another zero over here. Although it doesn't make a difference to the value, but adding a zero implies something to the reader of that data. He understands that you had an instrument that could reliably read the second digit. That is the zero that you are saying. You are writing a zero for a certain reason. If you are writing a zero, then it means your instrument had that capability. But actually, your instrument did not have that capability. So therefore, it becomes misleading if you add a zero after the decimal. Although it doesn't make a change to the value, but it is highly misleading. Don't do that. Also, if there is no digit before the decimal, then put a zero to make the decimal prominent. For example, 0.02. Put this additional zero to make the decimal prominent. And finally, at the bottom of the table, we have done the experiment many times, so you can find the average. The mean value of the quantity should be shown at the bottom of the table, right? Those are the steps in recording the data. So a typical tabular representation might look something like this. We have what is called a row heading, or sometimes it is called a stub, where you have row entries, right? And then you have a caption which is called column heading. Within the column, you may have subhead and you have something that you are measuring as the column head. And then here you may like to total all the rows, like all these entries that are here for a particular row, you may like to total it up here. For the next row, you want to show the total here. So that is the total of the rows. Then here, total of the columns, all the entries here, you can total it up here. All the entries here, you can total it up here. So you have a total of columns and total of rows. And then there are two types of tables. One is the column is headed and the rows are numbered. The columns are having a certain heading and the rows are just having numbers 1, 2, 3, 4. Or you have headed rows and numbered columns. Which one do you choose? It is based on convenience. So let us see some examples on that. Okay, here is an example. Look at this table. This this is a table for measuring what? What is the quantity that you're measuring? That is the diameter of the bob. Mention the instrument that you have used, that is using the vernier calipers. Mention the least count of the vernier that you have used, that is value of one main scale divided by number of divisions on the vernier scale, so many centimeters. Mention the zero error, if any, with the sign. So all this is the heading of the thing. Then you are doing many readings of the diameter. So observation number 1, 2, 3, 4, etc. So the rows are numbered 1, 2, 3, 4. The other rows 1, 2, 3, 4, 5, 6. And then you have column headings. The first column has got a heading main scale reading, which is the reading is called A in centimeter. Then you have the next column vernier scale reading. Within that, you want to separate it out and say which is the number of vernier division P that is coinciding with the main scale. And then you write the actual vernier reading, which is P into the least count. The least count has already been entered here. So P into least count gives us some other reading called B. And you have A here, you have B here. The observed diameter of the bob is A plus B, right, in centimeter. And then, depending on the zero error, we'll have to present the final diameter of the bob. We have many readings here 1, 2, 3, 4, 5. We write down here the average value of the diameter, which is the observed diameter, and the correct diameter of the bob will be observed minus the zero error, as we have learned earlier. So, final data conclusion of the table is presented right at the bottom. So, this was headed columns and numbered rows. So columns are made in the same sequence in which the data is measured. For example, first we measured the main scale reading, then we measured the P, and then this was just a calculation. So when you write the columns, they are written in the same sequence in which they are measured, and all like values are recorded in the same column. At the top of each column, which is the quantity that is being measured, is written along with its unit. For example, what are we reading? Main scale reading. What is the unit? Centimeter. And we are giving a name to it, A, centimeters. Now, the number of rows in the table would indicate the number of measurements that you made, right? So, another example of headed columns and numbered rows. This time we are measuring the time period. What instrument? You have to mention it using a stopwatch. Least count of the stopwatch, also you measure. Then the rows are numbered 1, 2, 3, 4. Then columns. For what are we measuring? The length we are changing, right? So for various measurements, we are changing the length of the pendulum. So what is the length? Unit in centimeter, and we're giving a name to it, L. Then we are measuring the time for 50 oscillations, and we are calling that time as small t, and the unit of that is seconds. So this is what we measure, and this is what we measure. After that, this is a calculation. Time period is t by 50. And then we also have the time period, and this is what we are calling capital T. And then we are also calculating L by T square in order to indicate something. So we may change the length in the pendulum. For example, first we start with 10 centimeter, then we do 15 centimeter, then we do 20 centimeter, right? Many readings we can take for the oscillations. And for each, we measure the time for 50 oscillations. And for each, therefore, we've got the time period. And this time period that you see would increase as the length increases, right? So presenting data in this form gives us a very quick grasp of the relationship between quantities. For example, we can see here that the time period would increase as the length increases. Not exactly linearly because there's a square root relationship, but at least we know that if the length increases, then the time period increases. Also, that if you do L by T square, since we know that T is equal to 2 pi root L by G, then square both the sides, that is T square is equal to 4 pi square L by G, and let me write it like this. Then L upon T square will be a constant. So for all the readings, whatever you write L by T square should be the same, a constant. The purpose of showing the last column is to say that the quantity L by T square remains constant, right? This is also headed columns and numbered rows. What about the reverse, headed rows and numbered columns? This time we have numbered the columns, observation number 1, 2, 3, 4, 5, and we're measuring the volume of a solid by displacement method. So that is the quantity that is being measured. The least count has to be also written of what instrument you are using, the least count of what instrument and how much. And then we have now headed rows. The first row is initial level of water called V1 and the unit is milliliter. Second row is headed final level of water after immersing a solid, that is V2 in milliliters. So this is what is measured. And the third one is calculated V1 minus V2. Okay. And we do many observations so that we can take the mean value of the volume of the solid, which is the ultimate goal of this particular experiment. Mean means take the average of all the five. So this was headed rows and numbered columns. So when you have the data now, you can present it in the form of a table, which gives you a quick grasp. But an even better method is showing it graphically because it tells us it gives us a visual idea of the relationship between quantities. The shape of that graph will tell us a lot of things about the relationship between the quantities. So we plot the graph between two quantities, between let us say y and x. I can take y and x. I'm just calling some quantity x and some quantity y. And when you plot a graph between y and x, it will show a relationship between those quantities. So here, this is called the x-axis. This is called the y-axis. And they meet at the point, this is called the origin. And the entire thing, origin and the x and y axis, that is called the coordinate axis system. Now, from the origin, this side is plus x-axis, the other side is minus x-axis, and for the y, upward is plus y-axis and below is minus. So if you suppose I say x is 3 and y is 4, then locate that particular point on the graph. How do you show that? X is 3 and y is 4. So x is 1, 2, 3. So x is 3, that means that particular point must be lying somewhere along this line. Now y is 4, so mark of 4, that means that point must lie somewhere along this line and the actual location becomes the intersection of those lines, which is x equal to 3, y equal to 4. And this 3 comma 4 is what we call the coordinate of the particular point. We always write x first and y second. So like that, suppose I say what is the coordinate of this particular point? X is minus 2 as you can see here and y is 1, right? What is the coordinate of this particular point? X is minus 2 and y is minus 4. That is the coordinate of that. What is the coordinate of this one? X is 1, this is plus 1 and y is minus 2. Accordingly, we have divided that in four quadrants. In the first quadrant, both are positive. You see, x and y, 3 and 4, both are positive. In the second quadrant, x is negative, like you can see, minus 2, and y is positive. And the third quadrant, both are negative. And in the fourth quadrant, x is positive and y is negative, right? So graphical presentation is a very good way of trying to communicate the relationship between quantities. Example, as we grow, our weight increases. I have put weight within quotes because normally in colloquial lingo we say weight is 50 kg, 60 kg. That is not weight actually, that is mass, as you know. So that is why I put that in quotes. As we grow, our mass changes, but does it change at the same rate? Meaning that do you add 1 kg every year? Not quite so, right? Sometimes you add 1 kg, sometimes you add zero point 0.5 kg, sometimes you don't add at all. And sometimes you may not add, but you may reduce also. So the plot of your weight versus the age will tell you how the weight increases or decreases or doesn't increase or decrease as the age increases. Age will only increase, age can never decrease. So the weight depends on the age. Put age on the x axis and weight on the y axis because x is treated as the independent variable and y is the dependent variable. Y depends on x, and when y depends on x, in some manner we say y is a function of x or y is equal to f of x, where f is some function. You're going to learn about function more in 11th standard, but essentially, when you say y is a function of x, it means y depends on x in some form. For example, if I say y is equal to x square, then as you increase the x, y increases. If you decrease the x, y decreases. If I say y is equal to 2x, again there's a relationship between y and x. But these two relationships are different. Y is equal to 2x and y is equal to x squared. They are two different relationships, right? And these different relationships is what we call different functions. All right. So the steps in plotting a graph are: take your graph paper, decide on your axis, decide on the origin, and then whatever the origin, x and y will be. X is horizontal, y is vertical. But the question is, where do you place the origin? In the middle? Or should we do it like this? There's the origin, there's the x axis, there's the y axis, there's the minus x axis, there's the minus y axis. How do we decide where to put the origin? The idea is this, that ultimately the graph that you plot should cover as large part of this graph paper as possible so that the picture is big and clearly visible to everybody. So if you have a situation that x and y are both positive, then we are only talking of the first quadrant, right? We are not talking of second, third, and fourth. X and y are both positive. In such a case, it is better to put the origin somewhere here so that you have the entire graph paper to plot your graph, right? So, what are the steps in plotting a graph? Give a title. For example, you will write here graph showing variation of something with something, right? Right at the top, you will write it. Select the origin and the axis. Put the origin at such a place that the plotted graph covers a large part of the page so that you have a big picture. Label the axis along with the units. On X, what are you plotting? On Y, what are you plotting? And also write the units. Select the scale. Now, what do you mean by scale? Suppose you're putting age on the x-axis. There are many divisions. So how many divisions represents 1 year? That is what is scale. So select the scale in such a manner that again, graph that you plot would cover more than half the page size just to get as big a picture as possible. And then the scale of x and y can be different. They need not be the same. The idea is to plot a big graph. So put the origin at the right place and select your scale properly so that it covers a large part. And then plot the points based on the reading that you have. And finally, draw the best fit curve. Right? Draw the best fit curve, meaning suppose you have only the first quadrant and you get some points like this, right? You get some points like this. So what is a curve? Is it this? There are always some random errors in everything. So one way is to say that, look, we could approximate it to something like this, a straight line that is a best fit curve, where some of the points are on one side and some of the points are on the other side. That is called the best fit curve. It need not be a straight line. It could actually be a curve also, but the best fit is that only. And again, about scaling, if the values are very large or small, then use some multiplying factor so that again the graph paper is covered as much as you can. Certainly, more than half of the size of the graph paper should get covered. Let's take an example. We know about the pendulum t square and L. If you have, then you get a straight line. And we have the observed data, the length in centimeter, right? And we measure the time period. We are plotting and we are writing the square of the time period t square in second square, and the length is in centimeter. So both length and time are positive only. Therefore, I choose my origin somewhere here. Which is the dependent variable? The time period depends on the length. Length doesn't depend on the time period. So length would be kept on the x-axis and write L in centimeter, write the units and mark off the scale. I have chosen the scale such that I write 20, 100, etc. Why did I choose this way? Because I see that the range of the length is from 20 to 100, right? I want to cover as much as possible. The page I want to cover as much as possible. Therefore, I've taken such big scales. And time period is going up till 4. So I choose my 1, 2, 3, 4 so that a large part of the thing is covered. And this 4 is in square seconds. And then we are giving the title graph showing the variation of square of time period of oscillations of a pendulum with its length, and then mark off all the points. 20 and point 0.8. Say 20 and this is point 0.8. Then 40 and 1.7. 40 and this is 1.5. So 1.7 is somewhere here. So like that, we have plotted all these points. And then we see that they are nearly in a straight line. We draw the best fit curve. That is the best fit curve, which is going to the origin. You can see that my graph is covering a large part of this graph paper. If I had chosen a small scale, then it would have been only a line like this, maybe. I'm only going from here to here. That is not a good graph. It should cover a large area of the graph paper. The other interesting thing is once you have the best fit curve, then we can find the value of y for any other value of x which was not actually used in the experiment. For example, in this case, x equal to 75 centimeter, the length of 75 centimeter, we don't know the time period because we didn't do an experiment with length equal to 75. We didn't do it. But now we can predict what it would be. Take length equal to 75. So this is 70 and 75 is somewhere here. 75 centimeter. And then on the graph, go to the graph and mark off that point. You can see what the time period square would have been. So this point is somewhere in the middle. We can interpolate or extrapolate. Interpolate means for a value like less than 20, if there was 10, then what would have been the value of t square? That is interpolation. And extrapolation is beyond 100 also. If the length was beyond 100 centimeter, then what would be t square? By the same graph we can read off. So that is the other advantage of plotting graphs. Now, if you have a straight line, we talk of the slope. So this is the same experiment, and we have the line. What is the concept of slope? This is a very important concept in mathematics and in physics. Slope is the rate of change of y, I should say, not rate of y, but rate of change of y with respect to x. That means how much does y change when x changes by 1 unit. So you are at a certain point, let us say, okay, you increase x by 1 unit, right? You increase x by 1 unit. increase x by 1 unit means that point is somewhere to the right, and that 1 unit may be somewhere here. So you have increased the x by 1 unit. Then, as per the graph, the y value doesn't remain the same. The y value goes up to some place. So this is the change in x, delta x, and this is a change in y for that delta x, right? Slope means rate of change of y with respect to x. That means how much does y change per unit change in x. That therefore the slope is delta y upon delta x. And delta y upon delta x for a straight line is nothing but if you take this angle, the tan of that angle. Perpendicular delta y by base. You can just say tan of this angle, call this theta. For a straight line, the slope is very simple. Let that line cut the x-axis. Find the angle that it makes with the positive direction of the x-axis. Take the tangent of that. Tan theta is the slope, which tells us how much does y change when x changes by 1 unit. Now, in this case, you can see as x increases, y increases. So the slope is positive. If y increases as x increases, the slope is positive. Here, x is length and y is t square. If you increase the length, t square is going to increase. That's the relationship between those quantities. That is the beauty of the graph. It tells you that if you increase the length, the t square will increase. And that implies positive slope. If y decreases as x increases, the slope is negative. For example, suppose between some two other quantities, we had a graph like this, which was a straight line like this. Okay. Clearly, if you go this way, the x is increasing, but the y value is decreasing. The slope of that is negative. So for this guy, the slope is negative, meaning that y would decrease if x were to increase. So what is the slope of this? Well, let it cut the x-axis. The tan of this angle, let's call it alpha. The slope is tan of alpha. And you can see here that alpha is more than 90 degrees and the tan of more than 90 degrees is negative. So slope is always the tan of the angle that the line makes with the positive direction of the x-axis. For a straight line, the slope is the same at all points. That means y changes uniformly per unit change in x. What do I mean by that? Go back to the age versus weight example that we talked about. If your weight increased by 1 kg every year, uniform, then it means that the rate of increase of your weight with your age is uniform. It is not that in 1 year it went up by 1 kg, in the next year it goes up by 5 kg, or in the next year comes down by 2 kg. There is no such thing. In every year it increases by 1, 1, 1, 1, 1. That is called a uniform change in y with respect to x. For a straight line, the slope is constant and it is the same at all particular points. But for a curve, the slope is different. Okay. So let us see here. Let me just rub this off. Let us see here what do we have for the slope for this particular line, right? Okay. So for a straight line, slope can be taken at any point or between any 2 points. Between any 2 points. So I'm just taking this point and this point, right? And I want to know the slope between these 2 points. Well, it is the tan of this angle theta. So this is the change in the y called delta y, and this is the change in the x called delta x. Delta y is how much? This value, this value is about 3.7, and this value is 2.0. So 3.7 minus 2.0, that is 1.7 second square. What is delta x? This value is 80 and this value is 50. So 80 minus 50, 30 in centimeter. The slope is delta y by delta x, which is tan theta. 1.7 upon 30, and this was second square per centimeter. That means we can write the value 5.67 into 10 to the power minus 2 second square per centimeter. That is the concept of slope. If you took any 2 points, say for example between this point and this point, The slope would be the same. That's quite obvious because the slope is simple, the tan of this particular angle, and that angle is the same. For a straight line, the slope is the same between any 2 points or at any particular point as well. So that weight versus age example that I talked about. So if you think about measuring the mass of a baby as it is born, the age is 0 years right now. The mass of the baby is 3 kg, right? Right from 0 years to 20 years, as a baby grows into a child, and then into an adult, we find that up until 20 years, the weight keeps on going up from 3 and reaches 60 at 20 years. And after 20 years, the weight doesn't change, stays constant up until 50 years. After that, the person starts to become older, so he loses weight. Now you can see here, guys, when y is increasing as x is increasing, that is a positive slope. And here y is not changing at all. As the age increases, the mass is not changing at all. The delta y is 0. And if delta y is 0, the slope is delta y by delta x. Let me write here. Slope is delta y by delta x. Delta y itself is 0. The slope is 0. Zero slope means no change in y, although x is changing. After that, after 50 years, there's a negative slope because as the age increases, the mass or weight of the person is decreasing. Right? Take an example from physics. Velocity is the rate of change of displacement with time. So I'm plotting displacement here and time here. If it is a constant velocity, this velocity is rate of change of displacement with time. So that is delta s by delta t. What is delta s by delta t? That is the slope of the ST graph. Just like delta y by delta x was the slope of the graph between y and x, similarly delta s by delta t is the slope of the graph between s and t. If the velocity is constant, then the slope is constant, and slope constant means straight line. Suppose the velocity is 0, then the displacement, whatever it is at some point, let us say s naught, doesn't change with time. As the time increases, also the displacement doesn't change, the position does not change. That means the body is at rest, zero velocity. Seen another way, the slope of this line is 0 because a line parallel to the x-axis makes an angle 0 degrees with the x-axis, and tan of 0 degrees is also 0, right? So learn to connect up things. This zero velocity is because the displacement is not changing from with time, right? But it also means that the slope of this line parallel to the x-axis is 0. And velocity is the slope of the displacement time graph. Third example, suppose the displacement time graph is like this, then the velocity is not constant because the slope is not constant. What is the slope at a particular point? So here is a very important learning. When you talk of a curve, then the slope changes from point to point. All right. So what is the slope at a particular point for a curve? Well, the answer is at that point you draw a tangent to that curve. So here, if I want to know the slope, I draw a tangent to that curve, and then the slope of that tangent is the slope at that point. So at this particular point, the slope is tan of alpha. At this particular point, I draw another tangent, and the slope at that point is tan of this theta. Clearly, theta is more than alpha. Therefore, tan theta is also more than tan alpha. That means the slope here, the slope here is larger than the slope here. And larger slope for an ST graph means larger velocity. That means the velocity here is more than the velocity here. That means the velocity is increasing with time. That means there is an acceleration. Therefore, these graphs are so important. They tell us a lot of stories. If we are able to comprehend, then we can tell a lot of stories. But if we don't know the concept, then we cannot talk much. This capability of reading graphs and analyzing them is extremely important in physics. Okay, guys, I hope it is clear. Another example of graph plotting. There's a law called Ohm's law in electricity, which says that the voltage and current are proportional to each other. The voltage is measured by an instrument called voltmeter. The current I in ampere is measured by an instrument called ammeter. And these are the readings, right? Point 0.2, point 0.4, etc. So these are the readings of voltages and currents. Plot the graph for voltage against current, right? Let's do that first. Again, I find that both voltage and current are positive. Therefore, it makes sense to choose my origin at the bottom left corner. I identify my axis. Y-axis is voltage. X-axis is ampere, is current in amperes. And then for that, I choose my scale, and I find that current only goes up till 3 amperes. So therefore, I choose my scale so that I cover my graph paper as much as possible. And then voltage goes up to 1.2. So again, I choose my scale in such a manner that we can cover a large part of the graph paper. And then all these points are plotted. Clearly, it looks like a straight line. And the best fit curve is this one. That is the first part, plot the graph. Now, use the graph to find the current I1 at a voltage V1 equal to zero point 0.3 volt. Let's do that first. Voltage is zero point 0.3 volt. What is the current? Well, from the graph, you can read that. Locate that zero point 0.3 volt here. Here, look at the graph. Locate the zero point 0.3 here, volt, and then find the point on the graph and then find the current there that turns out to be 0.75 amperes. Similarly, find the current when the voltage is 1.1. So locate 1.1 volt and then read off the current at that particular voltage that turns out to be 2.75. So this is 2.75 is being called I2 and 0.75 is being called I1. Then he says find the slope V2 minus V1 divided by I2 minus I1. So from this data, I2 was 2.75, I1 was 0.75 from the graph, and V2 is 1.1 and V1 is zero point 0.3. That gives me zero point 0.4. Volts, it is voltage divided by amperes, right? It is volt per ampere. And in electricity, that is called resistance, zero point 0.4 ohms. In other words, if you have a V versus I graph, the voltage versus current graph will be a straight line, and the slope of that line is the resistance. Okay. Finally, we deal with so many quantities. Some are scalars, some are vectors. What is a scalar quantity? Scalar quantity is one that has a magnitude but no direction. Example, mass, 5 kg, 2 kg. It doesn't have a direction. Or time, 2 second, 10 second. It doesn't have a direction. Or volume, 50 cubic centimeter, 1000 cubic centimeter, no direction. Speed, 5 meter per second. Which direction? That is not important. Speed is a scalar quantity. But there are others which are vectors, which have got vector quantity has got both magnitude and direction. So velocity has got a direction. Speed is a scalar, velocity is a vector. So if I say 5 meter per second, then I'm talking of speed because I'm only talking of the magnitude. If I say 5 meter per second towards the east, I'm indicating the direction, then I'm talking of velocity. So whenever you talk of vectors, you have to indicate both the things, the magnitude and direction. Otherwise, you're not describing the quantity completely. So you have other scalars and other vectors. You can see current, potential, temperature, charge, pressure, resistance. They're all scalars. Some vectors are electric field, magnetic field, dipole moment, potential gradient, temperature gradient. Temperature is a scalar, but temperature gradient is a vector. Gradient means how the temperature changes from one point to the other. Gradient. Then we have momentum, torque, weight, etc. So the point is, when you're talking of a vector, specify both magnitude and direction. Otherwise, it's not complete. Second, if two vectors are equal, then their magnitudes and their directions, both of them should be equal. Otherwise, they are not equal. Third, if a vector is changing with time, then either its magnitude is changing or its direction is changing, or both of them are changing. In other words, even if the direction of a vector changes, it has changed. The magnitude may not have changed, only the direction changed, the vector has changed. Such an issue is not there with scalars. So that completes this chapter as well, experimentation. Now, please do the questions from your ICSE textbook, and after that, the assignment from my particular course material. Okay, guys. So from here, we'll go to actual physics of motion, and we're going to discuss one-dimensional motion.